List. It's not actually a list. It's nonlinear anymore. So today we're going to be doing hash maps. Hash maps are this data structure which is going to be incredibly useful to you when you're actually writing your algorithms in job interviews everywhere. Most of the algorithms you're going to write on a job interview are going to be able to become faster using a hash map. It's just super common and super useful. And to explain what it is, I'd like to get into a motivating example. It's how I like to think of hash maps, and it's something that might be a good way for you guys to conceptualize it too, because it could be a bit of a hard concept to grasp. So let's do that now. All right, so our goal is we're returning to in-person school, right? So we need to have a way to find our classrooms and find where our teachers are holding office hours, for example. So how do we find the office of a teacher, given which teacher we want to go to the office hours of? That can be tough because, a lot of the people who are in this class have never even been on campus and don't know where any of these locations are. So what is a good algorithm we could use to find them? The first algorithm I'm going to propose, which will be our lowest solution before we improve it, is going to be this. We go like a street, as if we were on the street, and each place has a sign which says which teacher is in that room, right? And then you have to go through the street, you have to walk along, and you have to find where the teacher is. So you have to traverse it in O of n. Could anybody tell me, what would be a way we could optimize this algorithm to make it so that it'll be easier to find a teacher? Again, our goal is to help return to in-person classes. We're going to have office hours in classrooms. So we're going to have an algorithm for students to find the teacher they want to talk to. In order to do this, you want to do this quickly, right? You give each teacher a key. Yeah, that's the hash map solution, but how do we associate each teacher with a key? What can we do with that? Well, that's the challenge of the hash map. It's how do we do it so that we can know where a teacher is, just given who this teacher is. And we'll find a solution to this later on. But before we do, could anybody propose a faster solution to this problem, which is not a hash map, which would be just a better version of this? Could we do something? Could we sort the teachers or something? Could we do one of our searching algorithms to find them, to do it more quickly than just randomly looking?
Start at a building where you expect them to be.
Yeah, you could do that, and yeah, you could do basically a binary search approach, right? You could have door numbers for each door, and instead of just having the teachers be in some random room, you give each teacher a door number. And you say that, you're going to be looking for, Professor Julia, who is going to be in door number 34 or something like that. So then you'll go to the campus, you'll find some building on the street, and you'll see, okay, so this is door number 400. I have to go to the left. Or it's and then to the left, you get to door number 100. It's keep going to the left. Now we're at door 10, go to the right. That's a binary search. So your time complexity is going to be at worst log of the number of doors, right? So that would be a better algorithm. But now you see this is fast, this is good, but you still have to go from door to door and you still have to find it. It's not going through every single door, so it's better. But there is a better way, and it's actually really intuitive. It's kind of an answer that seems almost too abstract to be in computer science. It's simply to use a map, right? Because when we look at a map of a campus, we can literally see, for example, classroom of Professor Julia is going to be located here. And then we know exactly where to go, right? We can go straight to that room. And now a map is not something that's really easy to conceptualize into computer science. But before we go into the deep explanation of how a map works, let's just talk about how a map would work in real life. Right? You'd take a look at your map, you'd say, I'm looking for Professor Julia, who is in classroom 34. So I'm going to go straight to classroom 34. Right? That would be kind of the idea of a map. And in real life, the way we'd look through the map is we'd look through a piece of paper and we'd find, for example, where the teacher is, or we'd type their name into a search, right? So that's going to be our fast solution. We've got a map where we take we take as input a teacher who is going to be our key, and then we send that to the map, and the map gives us back exactly where they're at, right? So this is kind of the idea of the hash map. Instead of going through and looking through every classroom, you knock on every single door and you ask, is this Professor Julia's classroom? Instead, what you do is you go on your phone or you go on some sort of map and you see on the map, okay, so this is where the classroom is going to be. I'm going to go right to that classroom. So that's the difference between the search and the simple array and the hash map. Now the challenge of the hash map, actually there isn't that much of a challenge. It's a relatively simple algorithm, but really the core of the hash map is the actual conversion between this teacher or whatever object you want into a key which we can use to access the map, right? And keys typically are integers, and we'll go into the details of this in a little bit. But first, could somebody tell me what generally will need to happen here for us to be able to access the teacher from a map. Like, how could we possibly put this towards computer science? Like, how could we take this map analogy and how could we bring it into software? What would we have to convert our teacher into so that we can access it in O of 1? Well, you say into a key, but what do you mean by a key? Like, how could we convert our teacher with all the data in the array? Okay, well, how do we access an array? Like, what can we do in O of 1 right now? What do we know in computer science is going to be an O of 1 operation? Like, how could we get to a piece of data in O of 1?
You know the index of an array, you access it by index?
Yes, exactly. If you know the index of a given array, you know that you can access that array at that index in O of 1, right? So what we got to do is we got to somehow take the teacher and turn it into an integer, right? So let's just say that we have a very simple operation. In fact, I think this is how it's done on campus, right? I don't know if it's done on campus like this or not, but I'm pretty sure, if I remember right, like you might have the teacher's name alphabetically, right? And then the teacher's names are in alphabetical order. So if your name is A, let's say you get assigned to a room on the first floor. So the first number of your room number will be the position of your name in the alphabet, something like that. I guess it doesn't really work because we don't use base 24 for our numbers, but bear with me for it. Let's suppose that like the integer value of the characters in your name would correspond to your room number, right? That would be a way by which we could map a teacher's name to where they are. So that could be one method, right? And then just knowing the name, you can say, okay, so I know that this is Professor Julia. If G is like, with the 7th letter in the alphabet or whatever, then we can say that this is going to be door number 7, or it's going to be on the 7th floor, right? So that would be an example of a hashing function. Generally what we need to do is we need to see this arrow with the key on it? That's taking this object, this teacher, it's converting this teacher object into a integer, which is going to be used to access our map, which is an array, which is going to then give us the door, which is at that index. So that's one idea of a hash function. Now, there's actually any way of it. In this situation, our hash function, all it really needs to do is it just needs to convert an object to an integer. Like, could somebody come up with an example, maybe better than mine, of a way we could take a string and turn it into an int?
I mean, if we ignore permutations, you could add up the ASCII values.
Yeah, that would be a way to do it. And in fact, it's not a terrible way to do it either, right? Because it would still hash most names differently. It would be pretty rare, right, for two names to have the same sum of their ASCII values. So that would actually be a relatively valid way to do it, right? Or we could, for example, multiply each ASCII value by a number representing its index, and that way you'll have even less likelihood of it overlapping. And there's countless ways to do it. You can do a lot of different values, but even going with just summing the ASCII values of the characters in the name, you can be pretty sure that we'll have a number that's different for every person, right? Or at least that very few people would share the same number. That would be a good situation. But now how could we make it so that that number never exceeds the size of our array? Right? Because we don't want our map taking up as much space as just like every teacher possible, like every name possible. We don't want an array that big. That's going to waste so much memory. So what mathematical operation could we use to take those numbers and to kind of squish them into a smaller number? You can say log, yeah, but log is not, yeah, log will make them smaller, but you can't use log to say make a number specifically as large as x. Basically, we need an operator which takes a number n and makes it within the range of 0 to another number m, right? So you say modulo. So could you explain how would modulo help us with this? Like, how could we use modulo to make sure that our hash value never actually exceeds the size of our array? If we want range x, we can do key mod x. Well, yeah, exactly. So the modulo operator, for all intents and purposes, limits the maximum value of a number to whatever the other side of the operator is. So, for example, 13 mod 10 would be 3, because it's just the remainder when you divide by that number. And that will basically let us compress all of our values into something that's within the range of our array, right?
But wouldn't that fail?
Sorry?
Like, if you have two numbers that exceed, but like for whatever reason they have the same remainder on x, like 2x, 3x, wouldn't that fail by giving the same key for this two different things?
Well, let's actually see that. That's exactly what my next slide is on. So what happens if we have two keys which conflict, right? So does it increase the likelihood of things repeating? Exactly, it does. So This is kind of the trickier part of the HashMap algorithm. We do actually allow 2 keys for one object. For example, what if we have a really large campus and all the teachers are too afraid to go back in person, right? There's only a small number of teachers who come back in person. So we might have one teacher who might teach in 2 different classrooms. So when we look at our map, it might say, for example, Professor Julia might be teaching in FDA Auditorium and also in McDonald Harrington. And you don't know which of those 2 rooms the teacher is in because the key will conflict. Let's say both of them had a mod 10 value of 3. So we don't know which room that this is going to go to, right? Or I guess actually more accurately, we'll have 2 different teachers whose modular value is the same. We'll get into the specifics later. For our analogy, let's just think of it as one teacher with 2 different rooms that got hashed to them by accident. Well, how do we know which room we need to go to? We have to iterate through. So what we do, there's multiple approaches to this. You'll see them in Comp 251. There's open addressing, which is a big one, where you just hash it somewhere else in the table and then keep hashing it somewhere else in the table. Or you have chaining, which is the one I'm going to go into. So Comp 251, right at the start, you're going to go into this, open addressing or chaining. It doesn't really matter for Comp 250. Just suffice it to know, I guess I'll give you a bit of an early spoiler, that chaining is where at each index, right, when you hash something, you'll put a list. So for example, in the example of modulo 10, you'll have a list of things at index 3, which all have the value 3 modulo 10. Right, and then in that list, you just have to iterate through that list until you find your actual key. So you store a pair of keys and values, and you iterate through that list until you find your real key. So let's say we have 26 or 23 and 13 as our possible keys that conflicted and both hit the modulo 3 bin or hit the value 3 bin, right? We know that we're looking for key 13, so we just iterate through that list until we find the key, key with value 13. Out of that list, right? Does that make sense? We just store a list in the index, and then we just loop through that list. Now, that's going to still be great time complexity because chances are very few things will have that conflict. Usually, we're doing a much bigger modulo than 10. And in fact, usually our size will increase, right? So we'll have to do a modulo bigger and bigger number as we add more stuff to our array. So for that reason, we will actually have less bad time complexity as time goes on. So does that all make sense, right? Like we store a list of items in each index, and in that list of items, we will have, our keys, and it'll just basically narrow down our search, right? It's similar to bucket hashing. I think this is what you might refer to as bucket hashing. I know it as chaining, but you might refer to it as bucket hashing as well. We do call them buckets, yeah. So what do we need to have? Well, we need to have some sort of transformation. I guess we did cover this a little bit already, which takes teacher and transforms it into an integer, right? So this is one of our requirements. We have a teacher to an integer. We mathematically transform teacher space to integer space, which we've already discussed. We can do by doing a hash, for example, summing the letters in their name, and then moduloing by the size of our array. And then, we have the one teacher, 2 rooms problem. We're just repeating the slide, aren't we? Okay. So now, are there any questions about the whole teacher classroom analogy before we go into the actual implementation, like coding part of this section? Does anybody have any questions about the teacher analogy?
What happens if you create 2 keys for the exact same object twice?
Okay, so for example, you have, if your keys are teachers, you want this teacher to have 2 different values. That's fine. You can just have each value. Well, you'd overwrite the values normally, right? So you could have, let's say, a key of Julia. You would overwrite the value. So whatever value was there before, when you add it again, it just replaces what was there. You could implement it differently if you'd like, but I think the standard is you just have 1 at a time. Or if you wanted to, you could just put a list in your hash map. So you could say it's like a hash map of teacher to list of classroom, and then it'll be fine. It kind of makes this example I put here a bit oversimplified because this is actually not what happens. Like what's on this slide right now is not strictly true. It just kind of helps you conceptualize it. What would really happen if there was 1 teacher in 2 rooms is it would be a hash map of teacher and then list room. And you actually put pairs in the array. But we'll see that when we implement it, and we'll see that in future slides. This is just kind of to help conceptualize the very basic part of the concept that you will have to iterate if you have a clash. And explaining the pairs and everything just gets a little bit more complicated, so I saved it for later. So yeah, this is a bit of a oversimplification on this slide, just to get the idea across. And then we'll expand on that in the upcoming slides to actually put it into reality. How is a hash map different from a tree? Well, a hash map lets you access each element given a key and O of 1. Whereas a tree, you have to do a traversal. So in a tree, you only know is the left node or right node bigger or smaller in a binary search tree? Or if you consider a heap to be a tree, you could say that you know that the head is always the max. But a hash map doesn't care about the compare to value. It doesn't care about the order of these items. It doesn't matter at all. What matters is the equality of these items. So when you go in a hash map, you basically are able to associate one object with another. Whereas in a tree, you are able to add objects and kind of retrieve them in sorted order reasonably quickly. It's kind of two different purposes, right? So HashMap is always implemented in an array, never with a linked list. I'm not aware of any linked list implementation because the core of the HashMap is the O of 1 access to an element, right? The way it works is we have a transform of our object into an integer, and then using that transform, we can access our array in O of 1, right? So we get two O of 1 steps. We've got O of 1, teacher to integer, and then we have O of 1, integer to array element, right? Those are two O of 1 operations, which again add up to O of 1. So compared to a linked list would be much slower, right? Because in a linked list, to get a thing at a particular index is O of n. So it wouldn't really make much sense to do that kind of implementation for it. All right. So if there's any further questions, of course, you're welcome to ask them away as we go. But now we'll get into the actual more programming-y side. And now here, the analogies are not going to be kind of loose. They're going to be more true in this situation, like more strict. And here I've got kind of an example of how a hash map could look. For example, we're trying to create, in this picture, we're trying to create a map of emojis to their strings. And we'll see that a bit later on. But before we get into this diagram and everything, we should look at just this general information about the hash map. So first thing we want to know is, what is the point of a hash map? You use a hash map when you want to be able to associate objects and look them up very quickly. What does this mean? For example, if you have, well, in this situation, let's say you want to you would really hate emojis and you want to replace all the emojis in a string with their string associate. What you could say is you could put all your emojis into a hash map. Then you can map them to strings, and you could just say for every character in the string, if the character is an emoji, replace it with that string. And looking up that string will be O of 1 because you use the hash map, right? So that would be an example of an application of the hash map. It's replacing all the emojis in a given sentence with strings. All right. Then we'll get into more of the uses of hash maps later on. Then we also have the other names for a hash map. In Python, you might see them as dictionaries or as associative arrays. I believe those two things mean the same thing. It's just the curly brackets, right? And then you say it's a curly bracket dict, and then you know it's a dictionary, and you know that you can look up using an object as an index. So like here, you say the map at the index of bicycle is bike. So that's its kind of other names. If you did comp 202, dictionary, associative array. If you did ECSE 202, you've already seen HashMap, or at least you should have already seen HashMap, but I don't think you learned how to implement it, you just learned that it exists. But yeah, for comp 202, it's those. In Java, we also have hash table, which for all of your purposes is just a hash map. They have some differences, like one can contain null and the other can't, and one is safe for multi-threading and one is not. But in reality, for comp 250, you don't care about the difference. Just know that when somebody uses a hash table, for all intents and purposes, its use is similar to the hash map. And in C or C++, you can import, like, standard map or unordered map, and those should be the same effect as a hash map. So that's just kind of some things to know off the bat to get you familiarized if you already know those terms, or if you see them later on in your comp sci career. That's what those all mean, and that's how you could probably access HashMap in other languages. Now, going into a hash map, it's got a couple of important properties. It uses objects as indices, so it's like an array. It's basically just an array, where instead of the integer index, you have a object index, right? So it's just like an array. You just have an index as an object. Then it's got O of 1 mapping, which means that you can map any object to any other in O of 1. That means you can get an object in O of 1 given the other object, or you can insert in O of 1 as well. And you can check if it contains an object in O of 1, which is a very useful property. Now, could somebody tell me what benefit might we derive from creating a hash map which goes from integers to integers? So, is there any possible benefit we could derive from having a hash map that maps an integer to an integer? Again, we know that a hash map is just an array which lets you access its indices using an object, basically, right? It's nothing but an array where you can access an object as an index. So why would we ever want to create a hash map which maps integers to other integers, when we could just say it's an array? Because arrays already have an integer index. Karen says it's if the integers are bigger than the size of the array. Yeah, that's exactly why. So imagine we need to map really big integers to each other. We don't have that many of them, but let's say we need to map 2 million 3 billion, something like that. For example, we want to look up countries by their population, or not countries, let's say something else. We want to look up, I don't know, like some number based on some other big number. So we could look up, for example, the amount of fuel that an engine takes compared to the number of newtons of thrust it will output. So the amount of fuel might be like, a few hundred, the number of thrust might be, a couple million newtons or something, and then you create this map which will take these numbers, which are really huge. So you don't want to create an array of size a couple million to store one number of size a couple million, or like 5 numbers of size a couple million, right? That would make no sense. If we have an array of size 5, why should we have a million indices when all but 5 of them will be empty? With a hash map, we can simply hash those numbers, and we can have an array that is only as big as the number of elements in it. Then we can still have indices that are really large. Does that make sense for everyone? Like, we can have huge indices that all map into a relatively small array. And then, yeah, these huge indices, right? I'm just saying huge integers. But if you have the access to huge integers, you could basically represent any object as a huge integer, because, sometimes we forget, but we're on computers, right? And in these computers, at the end of the day, everything just boils down to big numbers. Like, everything is a binary number. At some level, no matter what it is on your computer, it all comes down to a binary number, right? That's all our computers can store. So, if we can store a big integer in our hash map, and we don't have to have a slot for every possible one, that means we can store just about anything, right? Because if the only thing we need to store is the hash value of a given number and then the hash pair, we can store any object. Because as long as we can store a big integer, we can store an object, right? Again, every object is like a big integer. Remember, your computer just stores zeros and ones. So everything is a number. So if we can store any number, that means we can store anything. Does that kind of make sense? So again, hash maps can be used to kind of compress our integer index. If we use an integer index in a hash map, we can have integers as big as a few million. We simply compress them down into the size of the array, and then we can fit any large numbers into the array, regardless of the fact that otherwise it would be an index out of bounds, and we don't have to take up that much memory. And then since a computer represents objects as just, binary at the end of the day, we can, at the end of the day, also just hash our objects down into numbers and then store them in the same way. So that's kind of the point of a hash map. Everything is a number, so let's just make those numbers small enough to fit into our array and use that to store things and access them in O of 1. All right, so those are the main properties of the hash map. Are there any questions about the explanation or anything on the slide or anything in general? All right. I'll take that as either you don't have questions or they're not ready yet, so I'll let you guys formulate those if you do have them and send them in the chat when they're ready. And I'll go on to the next slide, which just talks about a couple of the terms that we have in hash maps. So one of the terms we have is hashing. That's actually the process of taking any kind of object and turning it into an int. That's how we take whatever we have in our that we want to put into our array, and we turn it into our indices, right? So here on the diagram, I've got a picture of all these various emojis, which we are hashing in order to turn into those indices, which we are then using to access our array. So we can see here that what's happening is we have all of the objects, right? All of these various emojis, and since we really hate emojis, we want to make sure that all of our strings contain no emojis. What we'll do is we'll hash these, we'll turn them into numbers, and then we'll use these numbers to access our array. So here, if for example we want to remove the bike emoji, and let's say, okay, we're going through a string and somebody said, I love to, and then the bike emoji. We want to replace that. So we'll do a for loop for each character in the string. If the character is the bike emoji, which we've determined that it is, we will hash the bike emoji, which through our magical algorithm turns into the number 0. Then we know that at the index of 0, we have the string name for our bike emoji. So we can say that we can replace that with the string bike, right? So that is our hashing algorithm. It'll take an object, it'll turn it into an integer, and then it'll let us access our array. When two different objects will hash to the same value, so for example, if both bike and dog were to hash to 0, that would be called a collision. Now, there's multiple ways of dealing with collisions. There's, for example, open addressing and chaining. Open addressing will add an offset to your hash value and hash it again, and keep doing that until the index matches. Or chaining, which is what we'll go into, creates basically a list at that index and just puts everything into that list. Then when we should increase our list and when we should redo our hash map is determined by what's called the load factor. The load factor is a value which determines what is the maximum ratio we'll tolerate of size to items. So if we have 6 items and 6 slots, the load factor would be 1 because we have exactly 1 slot for each item, which means that we're likely to have a little bit of collisions, right? Because it's unlikely that every single object will map to a unique value, so we'll probably have some collisions. That means the lower that our load factor, that means the more items can fit into our hash map without colliding, and that means our better time complexity. Do all these terms kind of make sense to everyone? Again, load factor means that's the ratio of your size to your number of items, and the more items you have, that means that the more likely it is that 2 items will hit 1 slot. So you want to increase the number of slots so that multiple items get each their own slot. Does it all make sense? I will take your silence as a yes for now. So, yes, a collision occurs when there's 2 items that hit 1 slot. Load factor is going to be how we mitigate our collisions. We can say a load factor is our ratio of our size to the number of slots. If our size is exceeding the load factor times number of slots, that means that we have too many items for the number of slots. We have to increase the number of slots and redo the hashing for everything. All right, so now we can move on to the next portion of our slides, which will explain sort of how more terms in the algorithm work. A couple words that you might hear. It's not really overly important. What I mean is that these terms, like exactly as they're presented, are not super important to knowing them, but knowing them is super important so that you can understand what people say when they talk about hash maps. So a key is the object that gets hashed in order to find the index. Keys are, well, in our case of the teacher example, the teacher is the key. The key is whatever you use to access your map. So in this example here, the key is the bike, and the value is the string bike, right? The key is the emoji, and the value is the string. So a key is what we use to access our hash map. We can look up the value given the key. So given the key, we get the value in O of 1, right? Then we have value. The value is an object stored in the array, so our value is just going to be whatever our key can look up. So we can have our bike, and we will hash it to turn it into an index, and then we can access the value stored at bike in our array. So literally, like in our array, we have the index of, well, the hash of bike, which in Python syntax would actually just be map at bike, right? That would be our index. And we can access that, and then we can actually get the string from the emoji in O of 1, right? We just access the value given the key. A hash pair is a pair of a key and a value. So again, since we have these collisions, we want to sometimes use our exact key. Sometimes the hash is not good enough, so we actually store pairs in our array. So in reality, what's actually going to be in these array indices is going to be a list of hash pairs, which will contain, like for example, bike and string. And we'll actually look through that list of hash pairs and see which one exactly matches bike. So that's going to be one of our important things. And then load factor, again, it's the ratio of slots to the number of things in the map. Load factor is probably the most confusing thing in here, in my opinion. I don't know if you guys agree. But yeah, the load factor is just the number of slots compared to the number of things in our array. Are there any questions about any of these key terms? All right. So I've got a question for you guys, actually. How long would it take to get the key given a value? So for example, given the string bike, how long would it take to get the bike emoji? How long would it take to get a key given a value?
Or however many objects there's in the array list 0.
Well, how would we know which, because like, remember, there's not necessarily any relationship between the key and the value. They can be completely unrelated objects. Like I could have hashed the key bike to a cat or a dog or a bug or anything, right? There's no relationship between the key and the value. So actually, we might actually have to look through our whole array, right? Because remember, our formula does not touch our value. Our formula only touches our key, right? Our formula only hashes the key object. It only hashes the emoji. It never touches the string. So we could put any string we want into any index, right? So in reality, to get our key given our value, we don't really have any information, do we? We'd kind of have to just loop through our entire hash map to eventually find the key, right? Like we'd have to do a for loop, and we have to say for every slot in our array, and then for every for every list in our slot in the array, is the value this? Because again, there's not necessarily any relationship between the key and the value, and there's no real way to speed this up, right? Does that kind of make sense to everyone? A lot of you guys said O of 1, right? But remember, we're looking for the key given the value. So it's like a one-way operation, this thing, right? We can get the value given the key very quickly, but we can't really get the key given the value. Does it all make sense to everyone?
So is it the sum of all the inner objects of the arrays?
Sorry, could you repeat?
Like, is it O of the... It's like the sum of O of n, and you do it like for the m arrays?
It would just be O of n being the number of objects in the hash map, because we just have to iterate through every object. So does anybody have an idea how we could speed this up? How could we, if, for example, we're not a bidirectional map, we want to be able to get the value given the key and the key given the value. How would you guys implement it so that you could have both operations be O of 1?
Bidirectional fields.
You could, so you say somehow reverse the hashing or some bidirectional thing, but actually there is a really, really simple solution to it that seems kind of naive, right? So what could you guys think of anything? Remember, the hashing doesn't touch the value. The hashing has nothing to do with the value. The value is never touched by the hashing algorithm. So what could we do to make it O of 1 in both ways? Two maps. Yeah, could you explain how you'd use two maps to make it O of 1 in both directions? And good option, but yeah, could you elaborate on that? Like, could you explain how you would go about using two different maps to have a bidirectional hash map?
Every key maps to their value, every value maps to their key.
Yeah, exactly. You would just have two maps, one that goes key to value and one that goes value to key, and then you would then take those maps and you would simply say whenever you add the key comma value to one map and the value comma key to the other map. So this is kind of something somebody might ask you on an interview or a quiz or somewhere, and it's a kind of it's a question that kind of makes you overthink, right? It's a question that makes you think about all these possibilities, like doing the reverse of the hashing algorithm or doing any of these myriad other complicated things. In reality, the solution can sometimes be the most naive solution, which is literally just to create two hash maps and to just access each index, just to hash each index both ways, right? To just have two different maps. One goes value to key, one goes key to value, and then when you try to .get, you can just check each map if it has that key, and then easy peasy. So that would be a bidirectional map. You would just create two maps. All right. So that is that for this part. Are there any questions about any of the terms on this slide, anything like that? Any of the things we just talked about? For a bidirectional map, would the array have to be the size of the largest value? No, it wouldn't, because again, we hash the values, which means we take the modulo of the value and the size of our array. So our values, or our maximum key, like integer key, will be, its upper bound will be the size of the array. Because our hashing formula will be some magic modulo the number of stuff in our array. So if we take the example from before, where we sum all of the letters in the name, we can say that our hashing algorithm could be the sum of all the letters in the name modulo the number of slots in our array. So our upper bound for our for the index will be the size of our array, and we do that using the modulo operator. Does that kind of clear things up? All right, great. All right, so here is kind of the important methods we're doing. We're doing hash method. And to do this simply, you guys might remember when you did dot equals and IntelliJ auto-generated it, it also generated something called hash code. And that's actually something we're going to use. Every object in Java is required to override a method called hash code, which gives you their 32-bit hash value. So the biggest possible number that you can hash, it corresponds to also the maximum size of an array, and it's used in stuff like HashMap. The hash code method of a Java object will give you what the developer of that object decreed to be their preference for the hash value of that object. So that actually takes a lot of work out of it for us. In Comp 251, you'll go into more about how the hashing works, but in Comp 250, let's just say that our hash value can be given by .hashcode modulo the number of slots in our array. And hashcode can work in all sorts of ways. In fact, the example from before of just summing the letters of a string, would that be ideal? Probably not, but it does actually give you a hashcode that you could use. So we have hashcode, and we modulo the number of slots in our array, which gives us a hash value corresponding to that object and where it should be located in our array. We have a remove method, which simply looks for our key value pair and sets it to null in our hash map, given the hash algorithm. And we have the add method, which simply, or I guess the put method, if we're being formal, which puts the key and the value into our map using the hash method, right? So it'll hash it, it'll find the index, and it'll then place our pair at that index. So those are our core hash map methods. And there is our thing again. And now that we've gone through our core methods and everything, we can actually get into the Java implementation of it. So we can do that now. Let me just transition right over my screen share. And if you guys have any questions about the theory before we get into the implementation, now is your chance to ask. All right, so I'll take that as a no questions for now, but of course you're welcome to ask as we write. Let's transition on over to our desktop. Here, I've got my IDE already open with the project from last tutorial, which I will then will create a new project in. And why is it being, oh, that's not it, there's it. So, which we'll just create a new project here, and we will create a simple hash map. So let's do that. Bottom bomb, just JDK, whatever you want, just make it blank, and then we'll call it hash map. Finish this window. All right, so in our hash map class, we need a couple of objects before we get started. So, well, first I'll create my hash map class. Hash map class. Hash map. And the hash map will do something with the generic, because we always like the generic, right? And sorry about the webcam flashing, by the way. That's just my webcam being silly. I got to get a better capture card. But yeah, so here with our implementation, we're going to be doing something a bit unusual with our generic. What we're actually going to say is we're going to say k, comma, v, which means we have two generics. We have a key and a value, which we could actually say as our key value. We don't actually have to say kv, but it's just, you know, typically it's conventional for our generic types to have a one-letter name. And before we do anything with our hash map, we also have to create a class hash pair. So we'll say class hash pair. Key, comma, value. And then this class hash pair will have a key and a value. Right? It'll be that simple. It's just that very simple small class which will be containing in our hash map. So now we need a couple of other things. We need a, let's say private double. I'll just make it a lowercase double, private static final double, and this will be our load factor, so load factor, and I'll put it at 0.5 maybe, just so that we can have, it's a pretty standard load factor. You can put whatever you want. The smaller your load factor, the bigger your memory complexity and the smaller your time complexity. Then we'll have a private, we can use an array list or an array, but since an array will be more strictly sized, we'll use an array, so private array, but what will be array of? I think it should be an array of linked list of hash pair, right? So linked list of hash pair of key value array. Now I know that's a bit of a mouthful, so we have an array of linked list of hash pairs of key value. We'll call it map is equal to new, and then, oh, this is going to be such a slog, but boom. And it's going to be size, let's just say our initial size will be 10. And do we need these generics here? I think it may be that there's generics. Okay, perfect. So, yep, that will be kind of our hash map. Now those are, and also our size will be an important field. Private int size. Right, so these are kind of our core fields of our hash map. These are what we'll build our hash map from. And now, before we do much else, we need to be able to find the index of a thing. So we'll make that method. So we'll call it private static int hash key k. And what we can return is return k dot hashcode mod size. And this will give us, or mod, I guess size is a non-static member. So it's going to be the hashcode mod the size. It's going to be that simple. So hashcode does a lot of work for us. We just use it, you know, to get our index. And then we can use this hash method to add stuff to our array. So are there any questions so far about what we've done?
Okay, so hash will take hash code will give us like a 32-bit hash, and we're using size to remap it to 0.
Yeah, we're using it to remap it to however much stuff. Actually, it shouldn't be size, should it? It should be map.length. Sorry, or size equals 0. Yeah, I did this wrong here. It should be map.length. So we should remap it to the size of our array, our underlying array. So yeah, this method, it should take our hash code, which gives us a number representing the object. It's 32-bit because that's just the size of an int in Java. It'll take this int and it'll just generate a largest possible Java int, which also corresponds to as big as possible of an array. And it'll then modulo it to the size of our array, which here is 10. It can increase as well, right? So what this will do is it will take our hash code and it'll map it to something that is within the size of our array. It'll just take our hash code and turn it into a number which is small enough to be an index. Does that make sense?
Yes, thank you.
Yeah. Key, an object, return the index in the array. Now we have everything we need actually to implement our add method, which here we call put. So we'll call it public void put, and it'll take as input a k or a key and a value, right? So it'll take a key and a value, and it'll output indeed nothing. It'll just put that into our map. So the first thing we do is we can say hash pair, and it's going to be key comma value pair is equal to new hash pair, and we don't have a constructor for that yet, so let's just generate one. Boom, boom, generate constructor, which takes both arguments. Boom, boom, hash pair of key comma value. Now we can say if the key is null, we can just return, or if key is null, return. Now else, we will say, well, actually we don't need to do an else, we can just say if key is null we can return, because we don't want to screw anything up. And now we can say that if our size is greater than our load factor, well, I guess we have to say our double size. So if double size is greater than our map.length, also cast a double, map.length. Well, actually, no. If our load factor is greater than our, or is less than our map.length over size, then we have too many things and we have to rehash. So I'm just going to create a method call. I'm going to just put a call to rehash. We're going to write that later. So this is just going to increase the size of our array so that the load factor is met. So this increases our array size so that we can keep going fast. And rehash is going to be a bit slower. It's just going to remake our map with a bigger array. So we're going to have a rehash there. Now, all of this being well, we can say that int index is equal to hash of key. Then we can say that if our map at index is null, we can just set that to be a new map at index equals to new linked list, and it's going to be containing, or I guess, yeah, and then we can say map at index dot add pair. Right, so this is kind of our basic case. Now, else it's not null, so we can say for or if map at index dot contains pair. So if the map at the index does not contain the pair, but actually we don't care about the pair, so we actually have to do a for loop. So we can say for hash pair key comma value pair inside of our linked list. So for pair in list inside of our map at index, if the pair dot key dot equals key, if the key of the pair is equal to the key which we supplied, then, or I guess it's pair in list. If the pair in list's key is equal to that, then we just replace that one. Dot set or dot value is equal to dot value is equal to our value. And then we do this for loop so that we don't have any duplicates in our map. So we can set the value of it to that, and now here we'll also size, or we'll return, and we'll also do a size plus plus here. Now, if that doesn't happen, we'll just go into here and we'll say map at index dot add pair. All right, so what we do here is we basically make sure that we have no duplicates, and then we can also add to our linked list if it's not already there. All right, so this is kind of our add method. And everything is there any questions about anything we're doing in add here? Are there any questions about what we're doing in this method? All right, I guess I'll take it as no for now. So we can do what's called a rehash. So the rehash will say this happens when our size or when our load factor has been exceeded, our array is too small. So here we need to kind of remake our whole array using we have to basically remake our map with a larger array. So the first thing I can do is I can create a temporary array into which we will re-add all of our stuff. So let's just store our old one first. So we can say our we just want to get all of our values out. We want to get all of our pairs out. So we can iterate through this linked list of hash pairs, and then we can add those all to a list, and then we can basically redo our hash map. So we can say our let's just use an array list. So array list of hash pair of key value. A list is equal to new array list, and now we will say for or a linked list hash pair key value list of pair inside of our map, and then for hash pair key value pair inside of our list of pair list dot add our pair. Right, and that way we will basically fill our list with all of our hash pairs, and then we can say map is equal to new linked list, and then we'll make its size bigger, so we can make it twice the size it used to be. New linked list map dot size or mop dot length times 2. You can do this by however you like, and then we can say for hash pair key. Such a slog, right? This is why we use one letter abbreviations. Hash pair key value pair inside of list. We will add, or I guess put our pair dot key, pair dot value. Now this is probably not the most efficient algorithm for this, but it's okay, it's decent. value. Oh, and we also need to set our size back to 0 when we do this. So we can say size equals 0, just so our add doesn't make our size run away. Here we reset our map basically, we completely empty it out. And then we redo our putting with the larger map. So this will kind of make it so there's less collisions, and now we're modding a bigger number, right? So we've just doubled the size of our underlying list, and then we're going to re-add everything. So we basically extract all of our items, we create the new map, and then we put all our items back into the bigger map. And that way we have less load factor and better performance. So this is the rehash method. It's important when we're adding so that we can keep good time complexity, right? So that's one method. Now our final method, which we can implement here, is going to be remove. So it's going to call public void remove. Now we have key k. And this one's also, it's probably going to be our simplest method. Usually remove is our hardest method with all these linked data structures. Here it's going to be real easy. So what we'll do is we'll say, what is it? Int index is going to be equal to hash of our key. Now we'll say if the map at the index is null, we just return. Now if map, now we can do a for loop for everything in the map at the index. So for hash pair key value in our map at index. So for everything in the bucket, or I forgot to give it a name, pair. So if pair.key.equals k, we'll remove it, but first we'll say, what will we say? We'll say this is the one we want to remove, so we can say that we will say, oh, here we'll have to keep track of it. So we'll have to say hash pair key comma value to remove equals null. Now, because we can't remove while we're iterating, so we'll say if the pair is going to be equal to the key, or if the pair's key is going to be equal to the key, we'll say to remove is equal to pair, and then break. And then here we can say if to remove is not null. Now it's a bit of a janky method, like you could probably simplify this, but this is just how my quick programming is doing it. So if to remove is null, we will say that our map, or we'll say that our map at index dot remove to remove and size minus minus. So that will be our remove method. Are there any questions about the hash map and how it's running, how it all works, anything like that? All right, guess not. So I'm implementing chaining using linked list. Yes, I am. Java's linked list. Yeah, I'm just importing the linked list class from Java, and I'm using that. The reason I'm using linked list for chaining is that it works, right? Like you iterate through it. You don't really ever need to access anything in the bucket using its index. So I'm just going to use chaining using the linked list. All right, perfect. So here I'm just going to create a new hash map. This is the syntax for creating one. And it's going to count the number of times that a given string appears in like a larger string, right? So we can say that our, well, let's take an input. Let's take like the B-movie script. Can I put that into one string? Let's see. B-movie script. And let me just copy paste the B-movie script here. And we'll just break the B-movie script down into an array of strings so that we can add it all to our hash map, and we can count how many times each word appears in it. So let's just copy that. Boom, boom. The B-movie script. This is going to be really janky. I'm just going to put it into a string. So string B-movie is equal to, not that. Oh, does it not have shared clipboard? Oops. The entire B-movie script. Which link did I get this from? This one. Okay, let's just take all of that. Okay, like 5 minutes, this is going to be me copying the B-movie script. Come on, go. All right. Control C that boy. Control C. Now we can just paste that in there. Okay. So our bmovie script is that. This is really terrible. Like normally we'd want to take it from online, but yeah. All right. So this is sufficient. Now we can say string array words of script is equal to what is it? Bmovie script. Bmovie.split by the spacebar. So every time there's a space, we'll split it, and we can say our count dot put. Oh yes, we have to do a for loop. So for string word in words of script. What is it called? Count dot put. Or if count dot get. Oh, we don't have a get method. That's really silly of me. Hold on. Before we do this, we have to actually implement our get and contains methods, which was silly of me not to do. So we implemented remove, but not get. Let's just do this quickly. So get will be very similar to remove, except public value get key k will say return null if there's nothing in there. And now instead of to remove, it's to get. Actually, we don't even need to do that. We can just say boom, boom, boom. If pair dot key dot equals k, we'll just say return pair dot value. All right, very simple. And now we'll return null if it's not there. And here we can also say public boolean contains key k, which we'll just say similar to this, or we'll just say return get k is not null. All right, very simple. We got these methods. Now we can just say, now this is not readable code. I do not recommend you guys do this in your code when you write it. Count dot contains key word count dot put count dot get key. We got word plus plus, or was it word comma? So this basically iterates the counter for that. What is count dot get word get? Plus 1. All right, there we go. And else we'll just say count dot put word comma 0 or 1. Right, so this basically makes it so that we count up each word in the Boomi script for how many times it appeared. If we want to make it even more robust, we can say word equals word dot to lowercase dot trim dot strip. Just get rid of everything in there, make it lowercase, so that makes it easier. Now we can also say, or now we can just say that we want to check what's in our hash map. We can't do that very easily, so I guess we'll have to, we could sort the output of our hash map, but let's just say that we want to get the frequency of the word I. I should have more than one occurrence in it, so let's find I. System.out.println count.get I. Right, let's see this. So if I run this method, sorry about the unreadable code, let's hope it works. And let's hope that we're able to find how many times our words have been in the bmovie script. No, not pointer exception, iterator, because list of pair is null. Where is list of pair? Hash pair key value. Oh, it's not called list of pair. It's called pair. Oh no, it is list of pair. Oh, because these might be null. That's why. Pair and list of pair. Forgot a not null check. Oopsies. If list of pair is not null, then no, it still doesn't like it. Because list of pair is null.
Sasha, you wrote if list of pair equals null.
Oh, silly. My speedy shortcuts did not turn out well for me. A -10 out of bounds for this. Where is it? Map at index. Oh, so the hash looks like it went wrong as well. hashmap.length. Let's just make sure it's positive. Math.abs. This is a bit ratchet, but so be it. Boom, boom. And now finally, do we get an output? We should. Might take a second. No, out of memory error. Okay, so it looks like we're doubling our size too much. Let's just say plus. Yeah, 40. Yeah, doubling is probably not the safest. But yeah, there's a bit of issues with it because we are doing a really massive data set. Probably should have tested with something more reasonably sized beforehand. Or is there even enough memory to fill a map with the bmovie script? I guess we'll find out, shouldn't we? Why did I have to use such a massive test? Though it should be reasonably fast with HashMap anyways. Probably getting a lot of collisions. Okay, I might reduce the size of this string. Because we're probably getting a lot of collisions. It's probably not a very efficient hash map, so I'm gonna just like I'm gonna make the job a bit easier for it. It should eventually run, but it sure is taking its time. So let's just trim it down, give it a bit of help. And we can trim it down some more. Boom. Okay, now this should be a more manageable task for our puny little ghetto hash map. Eventually. Alright, maybe I should have done a smaller test before I did this. O of 1. Yeah, it should be O of 1 for access. It's O of n to rehash, though, so that could be one of our failings, is that our hash map starts too small. So we could do it like 1/10,000, right? And we can make it faster. It does O of 1 for all of the accesses, but it does O of n for the rehash, so that could actually be quite slow. And it does O of 1, or O of n for putting everything in the map and everything, so that could also be contributing to our slowness. There's a lot of ghetto things about this map, which are not exactly formally ideal. But really, it should be doing its job at this point. Let's just do a debugger and see what's going on. It might also be looping. For string word and words of script. Ba-doom, 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 ba-doom. It doesn't contain it. We put it. Aren't we assuring collision since the word I must be there a bunch? Well, actually, we are just, when I is there, what we're doing is we're getting the count and we're incrementing it by 1. So we're just putting an integer of increasing size in the index for that word, right? So we're not actually going to have that many collisions. But let's see. So our pair is there. This is a hash map. Its map is this with everything null. Let's see what happens. Our size is now 1. Is our load factor greater than map length over our size? Oh, we divide. No, our size is 1. So, it should be our size over our map length. That could be why. I think we're rehashing every single time. That would definitely cause some issues. Yeah, I think that was probably it. Because if we have to rehash it every single step, that must be O of like an insane amount. Okay, so that's actually much better. I found my mistake. So my size over length was actually length over size. So it had to make our array like colossal because it basically said that if our length was ever bigger than our size, we have to rehash. And rehashing made it always bigger, so it was rehashing every time it was adding. That made it ridiculously slow. So now I should be able to do this properly. Again, sorry about that little bug, guys. This ratchet hash map should work much faster now. So I was in this part of the string 7 times. Now let's count how many times I was in the entire script. O of words in the bmovie script. Yeah, no, that was much worse than O of words in the bmovie script. I think that was O of words in the bmovie script to the power of words in the bmovie script. So it was not exactly a good algorithm there. Whereas now, it's pretty good. It should be just O of the words in the bmovie script. Let's run the hash map and let's see. Yeah, okay, so that was much better. You can see how much faster it runs when we don't rehash it every step. I guess that's a lesson for all of you. When it's running slow, check your O of n methods. Because our only O of n method in this entire thing is rehash, and rehash was running too much. So, well, I guess lesson for me as well. But there are 211 occurrences of I in the bmovie script. And now we can try for any word. Let's say we try for B, and we can see that as well. And it should run quickly no matter what word we put, because it never has to search. It just hashes it. So B is in there 35 times. Sorry, that's another one. Let's see how many times sorry is in there. But yeah, you can basically have fun with this. And then if you sort by the number of occurrences, you could actually get a list of the words in ascending order. So how about Barry? That's just going to be our last little check. And of course, you could improve this by removing punctuation and removing new lines in the string. So you could say bmovie dot, let's say dot remove or dot replace period with space dot replace comma with space, or you can use some regex to just remove all the punctuation. That should make it even more accurate. So now if we rerun it, we should get better values. Anyways, so yeah, now that we removed the periods and the spaces, it matches Barry with Barry more, and I should be matched a lot more as well. Anyways, are there any questions about this whole HashMap thing, how this algorithm worked, how we're able to find all the words in the bmovie script, or how many times each word in the bmovie script occurred? This is a really common use of HashMap. In fact, this is taken straight out of an interview question, like how do you find repeated words in an array the most quickly? This is the fastest way. It's O of n. We literally have to add all of the words to the HashMap, and then we just simply check the count. Does it all make sense to you? Are you all keeping up with it? I can move on, and I can give you guys a quick little bit of tips for the upcoming quiz, which will be kind of on, well, all of the last content of Comp 250. Well, actually not even just quiz questions. I'll just give you a couple of quiz/interview questions, and I'll ask you guys to answer. I'll just do this quickly because I am overtime, but I will, I set out to do it, so I will anyways. And then I will get into the applications of all these things we learned in the next session, not bash. We want to get bash. All right, so the first I'm going to pose 3 different questions to you, which will be useful for you guys to know, because they're kind of what should be on quizzes and what might be in work. So one of the first question I'll ask you is, why use a heap when there is fast sorting? O of n log n sorting. So IE dot y add stuff to a heap when you can use a sorted array. Sorted array. So yeah, that's our first little question. That is quiz/interview. Why would you use a heap when you could be using a sorted array? Heaps have the property of displaying priority. Yeah, but don't sorted arrays also have that property? Like if you have a sorted array, you'd have the most large item in the first index anyways, right? So that doesn't really make any difference. Salim says it's better for certain applications, EX finding the minimum. Also, if you remove and add lots of items, it's more efficient. Yeah, could you tell me, what is the efficiency of adding or removing an item to a sorted array? So
if it's a sorted array, we have to like sort each time. However, with a heap, it takes, I think, O of n to add and remove stuff.
Yeah, exactly. Well, it's O of log n for adding and removing, but very close. And it is, yeah, better than a sorted list. So heap add/remove equal O of log n. Sorted array add/remove equals O of n log n. Right, so that's why we prefer the heap. So if we're doing something like the sliding window problem, you could use a heap or a DQ, but you could use a heap to improve it. Now, the next question we can ask is, when you insert something into a BSD, what does it look like? So question, what does a binary search tree, BSD, look like? Like when adding, let's say, 45, 20, 94, 55, 420, 53, 39. Right? So what does the binary search tree look like after you add all these things? So you don't have to give me the exact answer, but how would you guys approach doing these? Again, what does the BST look like when you add these items? Well, you just imagine you're adding these items, right? So you have to basically just run the algorithm in your mind. So imagine that you have a for loop where you say like, so answer imagine for integer in input, bst.add integer, right? And then you can imagine, because you know the BST algorithm, how that would look. So you could say, for example, it's going to be 45 at the root, then we say 20, 25, 20 is less than 45, 90 is bigger than 45, and you can get, you know, pretty quick at doing these, but these come up all over the place. This is going to be in your Comp 250 quizzes, your Comp 251 quizzes, they're just going to be all over the place. 55 is bigger than 40, but smaller than 90, so it goes here, right? And then 420 is bigger than 90, so it can go over here, right? And you can just keep drawing this tree. Eventually you can get fast at it, but these will come up all over the place. So just make sure you know how to manually add stuff to a binary tree. And if you want to check yourself, there is a very good site, which I'll link here in the Zoom chat, and probably in the video description for the recording, where you can visualize not just binary search trees, but all data structures when you do certain operations. So I've made this link, or I've put this link up in the chat for everyone. And on this page, you're able to add or insert, delete, whatever elements to a binary tree. And if you click on algorithm visualizations at the bottom, you can see all sorts of different algorithms and how they behave with different inputs. So that website would be really useful for you to check yourself, not just for binary search tree add, but for basically any kind of operation for any kind of tree. And it includes as well hash mapping and all of this. All right. So the next thing, our final little question that I'll ask that's kind of quiz/interview related will be one where I just ask for some pseudocode. So the problem is, so given an array of integers A, and a range, let's say R, find the index of the array where the range, where the sum of the items in the range is largest. So for example, this would be like, the array could be, 0, 0, 0, 1, 0, 1, 0, 2, 0, 0. This would be a simple example. So we wanted to output that within the range, which for example is 3. So R equals 3. Output will be, we want specifically the 0, 1, 0, 2, right? So it would be 0, it will be this thing up here. Except we also want to specify that we want it from 1, 0, 2. And then the sum, actually, instead of finding the index, let's just find the value. Yeah, well, we don't care if the ints are positive or negative. It's just the biggest sum. So find the value of the biggest sum in the array. Sum within range R in the array. It's a similar problem. I'll just make it a little bit simpler there. So here is equal to 3. So how would you guys approach this problem? Again, we want the best time complexity. And again, this is also just a very, very common interview question. And again, it doesn't matter if the ints are positive or not. It's just going to be any kind of ints with any range. What would be the best way to find the sum, the largest sum in the whole thing? Yes, proposed, we don't have to go into actual code, but any proposed pseudocode. Create a list with 3 sums. Create 3 lists with sums over the range. Find the largest number. Could you explain what you mean by that?
Okay, so the idea would be like, to, for example, take the first 3 numbers, sum them, take the next 3 numbers, sum them, repeat the same operations with a phase shift, for example, of 1. Do that another time, so we obtain all the phase shifts, and then all we have to do is look through our 3 arrays to find the largest number, and that will tell us where's the largest combination over the range 3.
I'm sorry, I'm not sure I understand what you mean by that. Like, our problem statement is that we have an array of any size, a range of any amount of numbers, and we have this range. So, for example, here the biggest one is 1, 0, 2, and we take the sum inside that range. So this could be anywhere. It could be 0, 0, 0, that's sum of 0, 0, 0, 1, that has a sum of 1, 0, 1, 0, sum of 1, right? We just move that range along our array. 1, 0, 1 has a sum of 2, 0, 1, 0 sum of 1, 1, 0, 2 is a sum of 3, right? We go like that. So Karen proposes that the largest is going to be the first three numbers for I is 0, I is less than size minus 3, I plus plus. The sum is equal to the array whatever, if sum is not largest. Or if sum is greater than largest, return sum, return largest. That would be interesting. So what's going on here? So I'm just going to paste that into here, and we'll see if we can analyze that. No, that didn't copy properly. Oh, it's copying between machines, that's why. Okay, so I'm not able to paste that in, but you suggest basically, like in terms of English, you'd say you want to iterate through the array, you want to do the sum. If the sum is greater than your largest, you just say that the largest is the sum and you return the largest. But how do you, oh, so you just loop through it and you keep track of that sum. And you sum along, but what if the window range is really, really big, right? Like what if you have a really long window? That's pretty good efficiency as well. But imagine you have a really big window and you want to keep track of its sum, right? So that would be a pretty long summation, because that's hard-coded for size 3, right? So you'd have to have an internal, so to make that not hard-coded, because the range can be any number, you'd have to do for I is less than the size, and then for every index, or for every size in the sum, you want to sum it, right? Like for every I is 0 to R, you'd want to sum it as well, right? Because it's not necessarily always going to be 3. You might have to do 2 for loops. So that would be one solution. For loops. So you'd have, for I in array, for I in, or for j in sum, or in range, or I guess for j from I to I plus range. Our largest equals, whatever. Would switching from the start of the index to the end help? Not necessarily. We could sort in a tree. Do you mean like, Salem, do you mean we could like use, because we basically want to slide something along our array, right? So we can sort in a tree intermittently and look for the largest parent-children combination. We could do that, but do we know a data structure where we can add and remove while keeping it sort of, yeah, we know the heap can do it, right? So we can slide a heap along it, but do we really care about which one is the largest if all we care about is the sum? Yeah, I had this on an interview once, or a similar question, and I also proposed to use a heap, but it turned out that there was actually a really simple solution for this. Like, we can think of very complicated data structure solutions for this, but just keeping it very simple. Is there some data structure we know where we can add and remove very quickly? A linked list. Yeah, well, specifically we want like a double-ended linked list, right? Because we want to, or we just want to stack, right? Because we want to be able to add from the start and remove from the end, right? Remember our snake game? We had the stack which just moved along our grid and it removed whatever was at the end and it added whatever was at the start. So how do you guys think we could use a stack to implement this solution very nicely and efficiently? Actually, not a stack, sorry, a queue. Not a stack, I meant queue the whole time. How can we use a queue to implement this kind of efficiently? So could we use a queue? All right, so imagine that we have to like slide our queue along the array. So we can say for I in array. Or I guess first we can say like queue from first R elements. For R I between length of array. Oh yes, queue from first R elements, sum first R elements. All right, so then we can say s minus equals q dot dq. Then we can say that s plus equals array at I. And then we can say q dot nq array at I. And then here we can just check our sum as we go. So we can say if s is greater than largest equals s. And this is completely O of n, right? Because we can see that we just basically use our q to maintain this kind of snake-like thing that goes through our entire thing. We just subtract from our q the one at array I, and then we subtract from it what we're removing from our queue, we're adding to it what we're adding to our queue, and then we're checking if it's larger. So imagine it like a snake that goes along your array. So imagine a snake going along your array. It eats array I, and removes array at its base. Right, and then it will sum equals sum minus base of snake plus array I, and then it just updates the sum based on that. So if you remember the game of snake where our snake moved along the grid, it's kind of the same as this, where the sum just gets updated as the snake moves along our array. And then we can even extrapolate this to a 2D or whatever, right? Because it's as simple as it's sliding our queue along the array and updating our sum. Does this method kind of make sense to everybody? I find it's a good example of how we can come up with really complicated solutions using queues and stacks and hash maps and everything. But sometimes the simplest solution is actually the fastest. And that is the little interview question example to wrap it up. Are there any questions about this or about anything else from today? All right, if there's any questions, I'll wait for a second or for any questions to come up. And if there are no questions, we can wrap up. But yeah, just gonna see for a second if there are any. Again, if you have questions of your own, I would be happy to answer on any Piazza or the next tutorials or during office hours. Good luck on your quiz and on your assignment, and I shall see you all later. Again, if any questions come up, you know where to ask them.